Okay, so yesterday we were looking at taking absolute value functions and writing them as what's called a piecewise function. And after a while, hopefully you're one of these people, you start to say to yourself, didn't we do this the day before? Like, what we're really doing is kind of what we did the day before, which is to fold pieces of a graph upwards visually, but then we're just writing it in a different way. So rather than saying we're simply going to fold the bottom half of the graph up, what we're doing is we're going to take the function and multiply it by -1 to flip it up, but we only want to do that where it's below the axis. So as an illustration here, everybody, forgetting about equations of functions, it doesn't really matter whether we have an equation or not. If I had the following graph, I better use a different color. If I had the following graph, it goes through the origin where x is 0. Let's say it crosses the x-axis here at x equals -10, and it crosses the x-axis here at x equals +9. And this is y equals f of x. Okay. If I were to sketch now y equals the absolute value of f of x, what we learned not yesterday but the day before yesterday is that the absolute value of f of x will look like this. This part up to here will stay the same because the absolute value is not needed. This point and this point, which have y coordinates of 0, well, the absolute value of that y coordinate will still be 0. It doesn't change. But this as well won't change. Does it ring a bell? There's nothing to do with piecewise functions just yet. This part, which I am going to draw and then peel it off so you can see what I've drawn. I've drawn this. That part, not including that x-intercept of -10, not including that x-intercept of 0, that part is all negative, so we have to flip it up. And it's going to, if I flip that up, I'm going to group that first. If I flip this up, it's going to be there. And this part here, which doesn't include that x-intercept of 9, is all negative, so it needs to be flipped up. And it's going to look like that. So this was the day before. This was just saying, look at the graph, and wherever it's negative, flip it up. Are you with me on that? Okay. Well, what you need to understand is that I'm going to have a whole bunch of colors here, so I'll use highlighters this time, is that this and this are the original, well, nope, my mistake. That yellow highlighted portion and this yellow highlighted portion, if I can get this to cooperate, and this yellow highlighted portion are on the original graph, right? We didn't mess with them. Which would mean that the absolute value of the function is equal to the function from -infinity up to -10, because we didn't need to flip it. So the absolute value of the function is just the function. It's also just the function from 0 to 9. The rest of the absolute value function, the green parts that are not highlighted, those are actually negative of the function to fold them up. And where does that happen? Where was the original function below the x-axis? X-wise, it was below the x-axis from negative 10 to 0. And it's below the x-axis, the original one, from 9 to infinity, which we can write as x is greater than 9. So that's what we added on yesterday. Your job sometimes is to find out where those x-intercepts are and to take the part that's in between the x-intercepts that's below and flip it up and write it. Bless you. So let's take a look at any questions you have. Does anybody have any questions here you would like me to go over? Go ahead, Lynette. I didn't catch that. I apologize. 4A? 12A. So 12A, in question 12, we're given a function. The function is g of x equals the absolute value of 6 minus 2x. And we want to create a table of values using those specific values for x. What does that mean? It means that we are going to use values of -1, 0, 2, 3, and 5, and put those numbers in for x to calculate the corresponding y values. I'll be honest with you, and it might be why you're wondering about this question. I don't really get the point of this question. I don't know what the big deal is about doing this. I'm not saying it's easy necessarily. I'm just saying I don't know where it's going. I guess it's going that in the place that they want you to sketch it using a table of values, which, I mean, let's be honest. We could do that on here. Anyway, what this means, Lynette, is that we are going to put in to the absolute value of 6 minus 2x, we're going to put -1 in and see what we get. And -1 times -2 is 2. Be careful, because that looks like 16, doesn't it? Is 2. 8 plus 2, 6 plus 2 is 8, rather. So we get 8. So the y-coordinate is 8. We put 0 in. You'll have 6 minus 2 times 0, which is 6. The absolute value of 6 is 6. Do you get the idea here? Do you want me to continue? Okay. I think the reason why they are asking you to do this, let me cut to the chase, okay? In this question. This is what is important, okay? So you have to be able to write y equals the absolute value of 6 minus 2x, which I guess I'll call g of x. You have to be able to write g of x in piecewise form. What this means, everybody, is you have to be able to figure out where y equals 6 minus 2x without the absolute value signs, where that graph is below the x-axis, because that's where you have to multiply the original function by -1. And I believe the reason they are asking you to do A and B is so that you can figure out visually where that occurs. But let me throw something else your way. We're really interested here right now in this function, aren't we? And we want to know where this function is below the x-axis, and we want to know where this function is above the x-axis, correct? It's a linear function, and I hope this makes sense. It's a linear function, which means it's going to have an x-intercept. Can we find that x-intercept? Sure. We set y equal to 0. We move the 2x over. We divide both sides by 2, and we get 3. So think about this for a second. The graph either will look like this, crossing at 3, in which case, when we write this as a piecewise function, the 6 minus 2x piece would be where x is greater than or equal to 3. I'm not saying that's correct. I'm saying if the graph looks like this, then when x is greater than or equal to 3, we don't need the absolute value signs because it's already above, right? Or the graph looks like this, right? There's only two possibilities. I'm not talking about how steep it is. Well, I know the graph looks like this because it's negative 2x, which means there's a negative slope. So we don't even need to actually graph the function. We can just say to ourselves, what would the graph look like in general? And according to this, when x is 3 or less than 3, y is positive. And that means when we write this as a piecewise function, we can just drop the absolute value signs whenever x is less than or equal to 3, and that means multiply by negative 1 wherever x is greater than 3. You don't even need to know all the precise details of the graph, just that it slopes downward through x equals 3. Any other questions? All right, so we are going to be moving on today and solving absolute value equations, which we're going to spend 2 days on. And the real reason why we learned what we have learned so far is because you need to know yesterday's content to do today's lesson. This is really the reason. I don't really particularly care if you can write a function as piecewise or not, but I care if you can or cannot solve an absolute value equation. And guess what you need to do to solve an absolute value equation? You need to write the equation in pieces. That's all. So when you solve an absolute value equation, you're going to rewrite the equation as two equations, just like you rewrite an absolute value function as two functions. We also hear, and I didn't put this in your notes for some reason, I would have to add it for next time, you really should be checking for extraneous roots. Remember what an extraneous root is. It's a solution that you get for the variable that you're solving for, and you get it in a way that's perfectly legitimate. You didn't break any mathematical rules along the way, but you're getting an answer that just doesn't work in the original equation. So we're going to solve the following equations. The absolute value of 2x plus 3 equals 8. And we're not really going to look at graphs here when we talk about breaking this into pieces. We're going to have to look at graphs if it's quadratic, and that will be tomorrow. So this is a little bit simpler. The bottom line is that this equation, 2x plus 3 as an absolute value equals 8, breaks into two pieces. It breaks into this equation, if the absolute values are not needed. In other words, if the thing inside the absolute values is already positive, then you just don't need the absolute values. But if what's inside the absolute values happens to be negative, then we would have to multiply that thing we were absolute valuing by negative 1 to make it positive. So these are the two equations we're solving. But remember, this is only when 2x plus 3 is greater than or equal to 0. If 2x plus 3 is greater than or equal to 0, then we just strip off the absolute value signs. We don't need them. They're gone. What we would like to do, though, is talk about what x has to be here. Just like yesterday when we had a function, but there's no y here. And really, 2x plus 3 is greater than or equal to 0. That's a pretty simple thing to solve. We would subtract 3 from both sides and then divide both sides by 2. And we have 2x plus, we have 2x then as being greater than or equal to negative 3, which means x is greater than or equal to negative 3 halves. I'm going to, just for the sake of explanation, label this as equation 1 and this as equation 2, because I want to show something to you with a number line. I'll go full screen so I can get everything in one view. This part on the left that says x is greater than or equal to negative 3 halves, on a number line, if I mark off negative 3 halves, what greater than or equal to negative 3 halves means is that. Are you with me? That's the set of values of x that we are allowed to consider for equation 1. I'm not really sure I need to do the same thing for the bottom one, but I will. This is when x is less than, this is when 2x plus 3 is less than 0. I hope it's clear that when you solve that, you're going to get x is less than negative 3 halves. Subtract 3, divide by 2. So for equation 2, and I'm just going to use a different color here. If you like, I can be totally consistent here and change this. I don't want that. Come on. Can I not grab that? Yeah, I can. I'm going to change that to red. Because then over here, what we are saying is for equation 2, those are the values of x. And we can even write that here. We can say x is less than negative 3 halves. And I'll tell you something here, because tomorrow is going to get more confusing. It is possible for you to be functional in solving these equations without even looking at these subdomains. But I expect you to be able to write out the subdomains. Which means if you're really confused by the subdomains and can't figure it out, you can still get the right answer, but you wouldn't get full marks. So we're going to solve these two equations. The first equation, I'm just going to go to a new page. The first equation is 2x plus 3 equals 8. Don't forget, this is only if x is greater than or equal to negative 3 halves. So we solve this equation. This is, well, easy. We subtract 3 from both sides and we get 2x equals 5. We divide both sides by 5. Boy, after making a big deal about how easy it is, I better not make a mistake, eh? And I divide both sides by 2 and I get 5 over 2. Yes? Okay. Let's check to see if it works in the original equation. The original equation, so this is just my check. The original equation was the absolute value of 2x plus 3 has to equal, what did we say? 8? So I'm going to put in I'm going to put in 5/2 for x. The 2's cancel. I'm left with the absolute value of 5 plus 3, which is the absolute value of 8, which is 8. So it's a correct solution. I just need to think about something for a second. Did we need, I had to make sure what I was about to tell you is true. Because there's something, a different area of math where what I'm going to tell you, it isn't true. And I wanted to make sure I had them sorted out in my head. Did we need to actually check to see if that worked? And the answer is no. What we could have checked instead is we got 5/2 for equation 1 is 5/2 in the domain for equation 1. Yes, so it's got to work. We could have checked it that way. If we solved one of these equations, and for equation 1 we got -8, well, -8 is to the left of -3/2, so it would not be in that domain I've highlighted in green on this page. The other equation that we have to solve, of course, is equation 2. My colors make no sense today. I understand that I'm all over the place. Equation 2 was taking that argument in the absolute value sign and multiplying by -1. That gives you 8. So we multiply that -1 through and get -2x minus 3 equals 8. I would probably move the 2x to the right side where it's positive, and I would subtract 8 from both sides and get -11. So x is -11 over 2. Don't forget that this equation is only valid for values of x that are indicated by that, where x is less than or equal, no, not less than or equal to, where x is less than -3/2. Is -11/2 less than, yeah, it is. It's in that domain. It's someplace over here, which means it will work. And you can put it in and check it in the original equation if you like. The original equation is the absolute value of 2x plus 3 is apparently supposed to equal to 11. If I take 2 times -11/2, I get -11, plus 3 is -8. Absolute value of -8 is 8. We're good. Any questions with example 1? Do you have a question, Isaac? Well, let me back up. You see that we're getting x equals -11 over 2. Okay. It's a correct solution, forgetting about the domain, because I don't think that's what you're asking about. It's a correct solution if it makes the original equation true. So on the left-hand side, when I put -11/2 in for x, that entire left-hand side has to end up equaling the right-hand side. So 2 times our supposed answer plus 3 in the absolute value sign. And maybe I'm not following what it is you're asking. So give me a minute to finish my thought, and then I'll touch base with you. When I multiply 2 times -11 over 2, I get -11. So what I have residing in the absolute value sign on the left-hand side right now is -11 plus 3. And -11 plus 3 is -8. So I have -8 inside of the absolute value sign. And I can see by you nodding, you get the point now. I think maybe I might have caused some confusion when I think at some point, and it might have been actually when I checked number 1, I didn't actually write 8 here and say they're equal. I just drew an arrow from the absolute value of 8 to 8. And if we did the same thing with the one we're working on in equation 2 from example 1, we get the absolute value of negative 11 equals supposedly 11, and the absolute value of negative 11 is in fact 11. So is that okay? Okay. Any other questions with example 1? So if you're following what I'm saying here, then when we take a look at the second example, which is B, we're going to have two equations. We're going to have to solve 2x minus 8 minus 2 equals 4x. And we're going to have to solve negative 1 times 2x minus 8 minus 2 equals 4x. And let's just imagine that you're very confused right now about that whole domain thing. That's okay. Can you solve these two equations? Yes. Can you take the answer that each equation gives you and check it against the original equation? Yes. So you can get the right answer. Let's do it that way first, and then I'll talk about the domain, which you're expected to know how to do for full marks. If I solve this equation, I subtract 2x from both sides and get 2x equals negative 10, which means equation 1 gives me this statement, x equals negative 5. Just double checking my work. Equation 2, I have an added kind of layer of work here. I've got to multiply that negative 1 through. So negative 1 times the 2x is negative 2x. Negative 1 times the negative 8 is positive 8. I'm going to add 2x to both sides to collect my x's on the right side, and I end up with 6 equals 6x, which when I divide both sides by 6, I get x equals 1. Okay, so let's check against the original equation. When I put negative 5 in the left side, I have 2 times negative 5 minus 8, then minus 2. And the 2 times negative 5 minus 8 is in absolute value signs. And on the other side, I have 4 times negative 5. So I'm putting in my supposed answer every place there was an x. That's all I'm doing. When I look at 2 times negative 5, that's negative 10. Negative 10 minus 8 is negative 18. The absolute value of negative 18 is 18. 18 minus 2 is 16. 4 times negative 5 is negative 20. Nope, sorry. Negative 5 is not a solution because we get a ridiculous statement, 16 equals negative 20. And I was going to say it's not even close. Not that it would matter if it's close, it's not equal. Now what if we check with x equals 1? Well, we would have 2 times 1 minus the 8 in the absolute value and then minus 2. And on the other side we have 4 times 1. Again, what's happening, I don't think I need to do this, but every little bit might help some of you, is I'm just replacing the x's with the answer that I think x is. 2 times 1 is 2. 2 minus 8 is negative 6. Negative 6 as an absolute value is positive 6. Positive 6 minus 2 is 4. And 4 is a solution because we get 4 on both sides. Okay. Now, I'm going to erase all my checking work here, so I'm just going to give you a minute to finish writing that down if you are. Looks like everybody's done. But the more sophisticated way to do this is to say that equation 1 is true if 2x minus 8 is greater than or equal to 0. Because equation 1 is the equation where we just erased the absolute value signs. We didn't need them. And if I add 8 to both sides, I get 2x is greater than or equal to 4. And that means that equation 2 is true only if x is greater than or equal to 2 when we divide both sides of that inequality by 2. And I hope you get used to the idea that equation 2 will always be true everywhere else. Right? Like it has to be true someplace from negative infinity to infinity. But equation 1 is already true when x is greater than or equal to 2. That means x is less than 2 is the domain here. Now, just think about this. And a number line is required for some people. I know not all. But x is greater than or equal to 2 means that. Is this number highlighted in blue greater than or equal to 2? Well, no, it's to the left of 2. So we didn't need to do that checking that we did where I erased it. This statement of x is less than 2 means that. And I better be careful here. You understand that the solid dot means I can include 2 and the open dot means I don't include 2. So over here, the number highlighted in yellow is 1. Is 1 in this subdomain that's allowed for equation 2? Yes, because 1 is to the left of 2. And we don't need to check it. This is a beautiful thing because if your equation is very complicated, your checking could get quite messy. Whereas if you can determine your subdomain, you just look at it and say yes or no. Number 3. So let's do this with subdomains. And this is an important one to do with subdomains. One of our equations will simply be 3 minus x equals 2x plus 1. And then we're going to write our subdomain. So this is what I refer to over here as the subdomains. And then our second equation, I'm going to leave room for us to solve the first equation. And I don't have room on my smartboard to put them side by side, but you might want to do that on paper. Will be negative 1 multiplied by 3 minus x equals 2x plus 1. And then we'll have a subdomain. I'm just curious, how many of you would have just written negative 3 plus x? Okay, yeah, and you can take that step. Then you don't have that extra step. So what is the subdomain? Well, for equation 1, have I explained to you as a group what the word argument means in math? I'm going to do so now because I'm getting tired of saying so much when one word does it. The argument in a mathematical operation is the thing you're operating on. So, for example, we're going to just take a quick break out of this. If I said to you that we have 41 squared, the argument, I think I've spelled argument wrong, but I'm long past caring. The argument here is 41. Because the operation is squaring, you're squaring 41, the argument's 41. If I said to you, we're going to do a mathematical operation of the sine of 12 degrees, the argument is 12 degrees. It's the thing you're operating on. It's the thing that the function is being applied to. The square root of 2x plus 1, the argument is 2x plus 1. The absolute value of 3 minus x, the argument is 3 minus x. So now that I've said that to you, and I repeat the same thing in 30-1 just in case somebody doesn't know, when I go over here to find out the restriction or the subdomain, what I want to say is it's where the argument is greater than or equal to 0, because the argument of an absolute value function must be greater than or equal to 0 if you're going to remove the absolute value signs. How do we solve that? How many of you would move the x over? I would probably move the x over, and I would get 3 is greater than or equal to x. But what is x then? If 3 is greater than or equal to x, what do I write for what x is? Well, it's less than or equal to 3. And there's a simple way to imagine this, and it's that, I'll throw this your way first and see how many of you can appreciate this. How many of you see that if you take this inequality that's highlighted in blue and you read it right to left, it says x is less than or equal to 3? Okay. Yeah, and that's not obvious to everybody. I could also do the following. I'm going to symbolize the number 3 with 3 lines to make my point. If I flip that over, left to right, look what it says. It says x is less than or equal to 3. How many of you would have moved the 3 over and not the x? Couple people. So if you do that, this is an important thing because it's just such a tiny thing that if you don't understand, you'll get the questions wrong. If you do that, you end up with negative x is greater than or equal to negative 3, so I have to multiply both sides or divide both sides by negative 1. And you're left with x and 3. But there's a rule that says when you multiply or divide an inequality by a negative, you have to flip the sign. Grade 8-9 math. But you rarely use it, so you forget about it. Bottom line here, these are our subdomains. Remember, everywhere else other than x is less than or equal to 3 will be the second equation. So you solve the first equation. This is 3x equals 2. I add x to both sides. I subtract 1 from both sides. I divide both sides by the coefficient of x, which will give me x equals 2/3. Let's just take a quick peek up here. Is 2/3 a number that is less than or equal to 3? Yes. We don't need to put it into the original equation. It is going to work. Solve the second equation by multiplying this negative 1 through first. Let's see, subtract x from both sides. You're left with x equals, subtract 1 from both sides, negative 4. Take a quick peek. This is your eyeball. Is negative 4 a number that's greater than 3? No. It's not a solution. It's called an extraneous solution. Go ahead, Kendra.
Say if I did want to put it back into the original equation just to be sure.
Yes?
Would I put it into that one or would I put it into the original one?
That's a great question. If you put it into this one, you'll discover that this equation is true. You always have to, though, put it into the original. Always. And it doesn't matter the myriad different types of equations you learn in this course or in Math 30. When you're checking, you always check against the original. So, what did we get? Negative 4? If I put negative 4 up here, which If you can't handle the subdomains, then you have to do it that way. You won't get full marks, but at least you get the right answers. If I put negative 4 up here, 3 minus negative 4 is 7, the absolute value of which is 7. If I put negative 4 on the right side, 2 times negative 4 plus 1 gives me negative 7, which is not what I got on the left. Have I answered your question, Kendra? Okay. All right. One last one here before we get to a different approach. Equation 1. I like a pattern here. I like doing the same thing the same way all the time. Then maybe it'll rub off on you, and you will always know that equation 1 is going to be where the argument is greater than or equal to 0. That's what I've always been doing. I'm saying we just drop the absolute value signs for equation 1. We'll put our subdomain in a second, but I want everybody to look at what I've just written. And I want you to think carefully about what I've done that's wrong. And it's a real tragedy if you make this mistake, because you can understand the higher level math, but you've made a grade 7 or 8 mistake. Anyone? I feel like that teacher from Ferris Bueller's Day Off. Anyone? Brody? Definitely. Because the argument 1 minus 2x, because that's a binomial, if we're going to subtract that argument, we have to subtract the whole thing. I know that says looks like cargument, but it means argument in brackets. The argument is 1 minus 2x is greater than or equal to 0. I would like everybody to find out what x is. So I want you to rearrange that inequality for x so that you can write what the subdomain for equation 1 is going to be. Yep, x is less than or equal to 1/2. I would probably just move the 2x over, and then when I divide both sides by 2, I end up with a half on the left of this inequality is greater than or equal to x, and I read it backwards. This part right here, I mean, I think you would have to show that on a written response, but that's only just a side project. You just have to take care of that before you can continue. That would mean that equation 2, which is where the argument is negative, well, if the argument is negative, then you have to take that argument and multiply it by negative to make it positive. And again, I know that's confusing. If 1 minus 2x was negative, then to make it positive, you multiply it by an additional negative, and we get that. This is equal to x plus 4. The subdomain here would be x is greater than 1/2. I really like the idea of the subdomain. You don't have to put the number in to check, although you could certainly put it in if you really want to check. I have to multiply that negative 1. Ooh. I got a mistake here, don't I? Boy, this is tricky. It's looking up here. It's 2 minus the absolute value. So I have 2 minus the absolute value. But the absolute value of a negative is negative 1 times the argument. In other words, I need to take just this for equation 2 and multiply that by negative 1, but I still have this subtraction sign there. Well, that's dirty. I can easily see myself missing that. Okay, well, that actually makes it pretty easy to solve because that minus and negative cancels and we don't need to worry about the subtraction at all. We get 2 plus 1 minus 2x equals x plus 4. Right? I better not do that. This minus times this negative becomes positive. What do I get here? Add 2x to both sides, I get 3x. Subtract 4, I believe I get negative 1. 2 plus 1 minus 4. 2 plus 1 is 3. Minus 4 is negative 1. So I get x equals negative 1/3. But x has to be greater than a half. Nope. Good. Did we check the other one? Oh, we never actually solved the other one, did we? I got so caught up in equation 2 that we didn't solve equation 1. That's okay. When I multiply that negative 1 outside, I get 2 minus 1 plus 2x equals x plus 4. I'm going to have to cram this in. I'll do it this way. I subtract x from both sides to get x. 2 minus 1 is 1. 4 minus 1 is 3. So I get this. Go ahead, Kendra.
It's not a negative 1. It's 2 minus, in brackets, 1 minus 2x. It's not negative 1.
And what I've actually done here is I've taken that negative 1 and I've multiplied it through. And I've taken that negative 1 and I've multiplied it through.
But it's not a negative 1. In the question, it's 2 minus.
Right? I understand what you're saying. You're saying there's no 1 here.
No.
Right. But if I can just ask you to focus on 1 minus 2x for a second. 1 minus 2x is a thing, right? If I multiply a thing by the number 1, does it change it? No. So maybe, in other words, I didn't do anything wrong there, actually. Okay. You might have been taught to peel off these brackets. And this is what I need to find out, by saying when you're subtracting something in brackets, you remove the brackets and switch all the signs.
I don't know. I didn't do it.
Okay. So there are 2 ways for you to go from this to this, which is what I wrote. And we need to talk about this because it's a skill from an earlier grade that we're going to encounter again and again and again. Are you sure?
Because 2 minus 2x is 2 plus 2x. Or
Yes. So, and that's what I was going to say. That 1 that I put, I'm going to get to it, and I want to finish this discussion because it might have opened up some confusion for some people, and I want to clarify it. When I do this, I just say I'm subtracting everything inside. So I say I've got 2, and I'm subtracting 1, and I'm subtracting negative 2x, which is what you just said, right? Which becomes that. And some students get confused by that. So some teachers, how many of you have been taught that you can put a 1 there and multiply that negative 1 through? A couple. So that's what we're doing. We're multiplying this by that and this by that. But anyway, we're back on track. We're good. Okay, good. So when I subtract x from both sides of this equation, I'm left with x on the left. When I subtract 1 from both sides, because 2 minus 1 is 1, I'm left with 3. X equals 3. Is 3 in this domain? No, it's not. So this is not a solution. That was not there's no solution. What does this mean? It means that these two statements can never be equal to each other. There is not, you could spend your whole life trying to find a number that you could put in for x to make them equal, and it can never happen. It's impossible. Any questions with D? All right, so we are going to solve graphically now some things. What does that mean, graphically? Well, we have solved some things graphically, quadratic equations. I think the best way to solve this graphically, there's two ways, but I think the best way is to graph y1 equals 2x plus 5 and y2 equals 3. There's another way to do it, which I can show you in a bit maybe, but I think this is the simplest approach. So if I go to y equals and clear out anything here, I can put 2x plus 5. Well, no, absolute value of 2x plus 5. Let's just, for kicks, take a look at what this thing looks like. Zoom 6. There it is. We can also graph y equals 5. Before I find the solutions, how many places do these two functions cross? 2, right? I don't know if you noticed, but if we go back and look at question, it's not the same as question A. That's okay. It crosses in 2 places. And that means we're going to have 2 solutions. And I will tell you right now, how come I put what? Did I? I made a mistake. I should have put 3. So I put 5 because I made a mistake. There are going to be 2 solutions here, and I will tell you right now that you can see there's 2 solutions. If you were to solve this algebraically, you'll get 2 solutions. Okay? You have to get the right number of solutions that matches the graph. And I'm going to do something else with that in a second, but I'm going to calculate by going to my calculate menu the points of intersection, go close to 1 and hit enter 3 times. -1 is a point of intersection. We're looking at the x coordinate though. We don't care about y. So one of the solutions here is -1. Let's do the same thing for the other point. Intersect. You just have to nudge your calculator and remind it that we're after the other point, so you go closer to it. And the other point is -4. Now, do you need to check these? No, because they do cross. Okay. Does this look familiar? Was this one of the questions that we did? Did the question that we did here have one solution and then one extraneous solution? Okay. Can you tell me, please, Danielle, what was the value of x that was a solution? 2/3. And what was the value of x that was not? -4. Thank you. All right, so I'm going to solve this graphically by graphing y equals the absolute value of 3 minus x and y equals 2x plus 1. Looks good. There's the absolute value of 3 minus x. There is 2x plus 1. Will this red graph and this blue graph intersect anywhere else other than here? No, because you can see these two lines are diverging away from each other, which means since they intersect in only one place, guess what? There's only one answer. And if you find the x-coordinate of that point of intersection, it's going to be the 2/3. But the -4, well, nothing's happening at -4. Well, of course nothing's happening at -4 because -4 is not a solution. The scary thing is I can ask you on an exam for the extraneous root, which means you have to solve it algebraically to find out the number that doesn't work. Anyway, you're going to get 2/3. By the way, what we're doing here, you can solve any equation like that. Absolute value, quadratic, linear, cubic, trigonometric. Were there only A and B in that last example? Or was there a C as well? That's it? Okay. So not a lot to practice here. Really force yourself to try to figure out that subdomain issue. It's really easy. You rewrite, without the subdomain, it's easy. You rewrite the equation without absolute value signs and you solve that. And you rewrite the equation without the absolute value signs, but you multiply the argument by -1 and you solve that. But try to get the subdomains involved in this. One way or another, you have to weed out extraneous solutions.